Up until now in this course, we've largely analyzed vectors, motion, acceleration, force, etc., using very simple cases in which the vectors act either in the horizontal or the vertical direction. However, you can easily imagine many cases where vectors are applied, forces are applied, motion occurs at angles, at some of the infinite angles between 0 and 90 degrees, and that's what we want to look at today. For example, you can imagine a gymnast who's hanging from a bar in which the tension in the gymnast's arms are in the vertical direction. But if the gymnast spreads their arms further down the bar, then the tension in their arms will be at some angle. Similarly, if you're towing an object and the point at which you're applying the force is different from the point at which the towing rope or bar is attached to the object, that force will be applied at some angle to the motion of the object. Today we're going to use the same geometric and mathematical techniques we learned yesterday to move between polar coordinates and Cartesian coordinates in order to analyze this type of more complicated motion in 2 dimensions. And as usual in physics, we'll start with a very simple example called the inclined plane. Now, what is an inclined plane? I'd like you to formulate an answer to that to yourself for a moment. You, of course, know that inclined planes involves angles of some sort. And that when you're on an inclined plane, that can affect your motion. Everyone has ridden a bicycle, and you know what happens when you crest over the edge of a hill and get onto the steep part. So let's take a look at this and see if we can specify this situation physically. Well, let's begin as usual by looking at the physical situation. Here we have a nice horizontal plane. Now we have a device for changing the angle. Let's start out with a simple example. We'll use a skateboard because that allows us to neglect the force of friction. Now take a look at this skateboard. It's sitting on the surface there. It's got next to no friction. Why isn't it moving? Can you specify that physically? That's right. We know it's because the force of gravity is pulling down on that. But there's a normal force exactly equal to that pushing up from the table. Hence, there is no net force, and it. Now, we've specified physically why that's not moving. According to Newton's first law, if there's no net unbalanced force, it will remain at rest, and that's what we have. Now, what happens when we start to incline the plane? It takes very little. What is causing that to move? Okay, we know that it must be an unbalanced force of some sort. And where does that unbalanced force come from? Well, has the weight somehow increased? No, we know that the weight stays the same. And in fact, it stays in the same direction, directly toward the center of the Earth. What's happened, though, is that by inclining the plane, a part or a component of that gravitational force begins to move along the plane. And another part or component is perpendicular to the plane, such that the normal force, in fact, is changing, and there's a slight gravitational force pulling the object along the plane. And because this is frictionless, it moves fairly fast. Now that's pretty clear, and you've all experienced that on a bicycle. You start to go down a hill and you suddenly pick up speed because you can feel the force of gravity. But let's try it with another object so we can continue to specify the physical situation. In this case, we've inclined the plane, but it does not move. Why is that physically? That's right, we still have gravity operating exactly in the vertical direction downward. We now have a portion of gravity, or a component of gravity, acting along the plane. But in this case, there's a frictional force acting against the motion and the force, which is balancing that such that the object does not move. What happens if we continue to incline the plane? The object is still in equilibrium. It's still at rest. Still the forces are completely balanced. We have a normal force balanced by the component of gravity acting through the plane, and we have a frictional force that's exactly balancing the component of gravity that's pulling the block along the plane. What will happen if we continue to incline? Okay, what just happened there? Express that to yourself physically. Satisfy yourself that you can put that into words. Let's look at it one more time. Okay, as we continue to incline the plane, more and more the component of gravity moves along the axis. And that's the story of the inclined plane. Now what I'd like to do is go back to our note sheet, and let's start to really specify that and look at how we can use polar coordinates and Cartesian coordinates to easily analyze this situation and then predict this kind of motion. Okay, so what is an inclined plane? Given all that we've just looked at and observed, what can we say about an inclined plane? Okay, an inclined plane is a plane that has a non-zero angle to the horizontal less than 90 degrees, such that part of the force of gravity acts along the plane and part of the force of gravity acts perpendicular to the plane. Oh, did you want me to repeat that? Okay, an inclined plane is a plane with a non-zero angle to the horizontal but less than 90 degrees. Because if we go up to 90 degrees, then it exerts no more normal force and the object is in free fall, such that part of the force of gravity acts along the plane to pull the object down, and part of the force of gravity acts perpendicular to the plane. Let's stress the parts that we need to be clear on. A component of the force of gravity acts along, and a component acts perpendicular. Now, we're in a good position now to answer the rest of the, or to lay out the rest of the questions in our guided note sheet.